So welcome back, everyone. So we're very happy to have the third talk today by Jurco from Prague, who's going to tell us about correspondences of quantum L-infinity algebras, BV theories.
Oh, thank you so much. Yeah, Hisham, for your kind invitation and for this great conference event. As you see, I am compromising between real slides and the Blackboard talk. And so this is based on some work in progress with Jan Pullman and Martin Zika. Okay, so I assume everybody here in the audience have heard already knows about BV theory, maybe not about quantum L-infinity algebras, but yeah, the point of view in this talk is they are the same things. And so if you know about one, you know everything about the other one. And here is the setup and the kind of vocabulary, the translation between these two settings. So what I have a differential graded vector space. Okay, for some technical reasons, I should assume that it's degree-wise finite dimensional. But the degree is, right, you know it from Batalin-Wilkowiski. It's the, yeah, you have fields and anti-fields, and they have different degrees. You have natural Z grading. We have the odd symplectic form, which is degree -1 for Batalin-Wilkowiski theories. And we have the BRST operator, the free BRST operator. So this is our differential. And it is compatible with the symplectic form. So the first kind of statement, or the correspondence between Batalin-Wilkowiski theories and quantum L-infinity algebras is this one. So if you have a solution to the quantum master equation, which you expand in the power of h bar, so it is a solution really to the quantum master equation. Then, well, this expansion, it is just like a sum of polynomial in your fields with coefficients. And well, these coefficients you can view as maps from the symmetric algebra, graded symmetric algebra on your vector space. So this is the, let's say in string field theory, this would be the state space of the first quantized string in your field in R or C, which are degree 0. So if I introduce a homogeneous base of my vector space V and the dual space, the fields, yeah, well, there is some more notation you are familiar with before I jump to the L-infinity relations. Because we have symplectic form, with the inverse of it, we form the Batalin-Wilkowiski Laplacian and Batalin-Wilkowiski bracket. And of course, as always, your action separates in the free part, in the quadratic part, which is formed by the free BRST charge and the symplectic form and the interaction part. And then, once you have a solution of the quantum master equation, which you can express in whichever way you like, then the translation to quantum L-infinity algebra is just the algebraic relations which follow immediately from the quantum master equation on these functions from the symmetric algebra on your vector space, your field. So, and you can write them explicitly. So you just plug in the expansion of S in the fields into quantum master equation and collect together degrees of h bar and the number of inputs, or the polynomial degrees, and this tells you that you have some relations between those coefficients in the expansion of the action. So you can forget, if you like, everything about Batalin-Wilkowski, and if you are a mathematician and you would like to talk about quantum L-infinity algebras, that would be your definition. If it's a collection of maps, graded symmetric maps, multilinear from your vector space, well, in C or R, which fulfill these algebraic conditions. And if you are maybe more familiar, not with the quantum version, but with the classical version, so you can consider G, which plays the role of genus, because it comes with powers of h bar in the action, and you get what is called the cyclic L-infinity algebra, which is an ordinary L-infinity algebra which has a cyclic structure, which tells you that you have to treat in your quantum field theory, like in string theory, well, democratically inputs and outputs. You don't distinguish between these. And okay, so maybe, okay, if you have seen L-infinity algebra relations, usually these are formed, you know, like generalizations, let's say, of differential graded Lie algebras or Lie algebras. So you maybe are used more to the language of operations. Since here we have functions, but we have also this non-degenerate symplectic form, this uniquely determines these M's, which are now maps from the symmetric powers of V into V, which you really can think of operations. So you have something which eats n-1 inputs and produces one output. So these are the higher brackets, like. And of course, the algebraic relations for F translate equivalently to algebraic relations for these operations. And if you forget about powers of h bar, so you put G0 and forget about cyclic structure, you get the ordinary L-infinity relations, which you are maybe more used to. So you can continue in translating things from Batalin-Wilkowski to L-infinity setting, or vice versa. What you do in quantum field theory, if you have a BV theory, or essentially any quantum field theory, which you can recast in the BV language if you like. You don't have, but you can, even if you don't need. And then you do BV integration, which gives you the S matrix, which, if you wish, you can view as an effective action W, which is a function on the cohomology of the BRST operator, of the free one. So this is what you do on the quantum field theory side in the BV formalism. What mathematicians do in the homological algebra setting, in the L-infinity homotopy, like L-infinity algebra setting, they do minimal model. This means they do transfer of the structure of the L-infinity of the homotopy structure from your original theory or from your original vectors, underlying vector space, to the cohomology of Q, which goes under the name of the minimal model. So the slogan would be that the effective action, or S matrix, is the same thing as a minimal model for a mathematician. And so actually you can say even more. Here in the physics side, you would say that your action is equivalent, just by field definitions, to the sum of a free action and of an effective action. But as I said, this is now only a function on the space of the physical state, right? So really on the cohomology of the free BRST operator, which in mathematics is formulated as a decomposition theorem for a quantum L infinity algebra into the minimal model, the minimal part, which is this L infinity algebra with zero differential on the cohomology, and the part which has only here quadratic action, so which is only differential, but there are no higher brackets, no higher operations, which is, okay, this decomposition. Okay, so maybe I can tell a bit more about this. So since we have our free BRST operator, we can look into the composition of our differential graded vector space, into the cohomology of Q. Then we have the image of the Q, and we can, okay, we have like the symplectic complement of the image of Q. Well, what we have is a partial inverse to the Q, so we have another part C, and our symplectic, differential graded symplectic vector space decomposes into two symplectic subspaces. One is the cohomology, and the other one is this C plus B. So these are now Lagrangian subspaces because of the compatibility of Q and its partial inverse with the symplectic form. C and B are Lagrangian subspaces, and yeah, they are complementary. So together they form symplectic subspace of V. And correspondingly, since the Batalin-Wilkowiski delta and Batalin-Wilkowiski bracket are formed actually using symplectic form, the inverse, they decompose also correspondingly. Now, what we do in mathematics, as I said, instead of computing Batalin-Wilkowiski path integrals, is that what we have actually from the beginning here, we have something which is called special deformation retract. So we have our original differential graded vector space with the free differential, with the free BRST operator. We have projection to the cohomology, and we have inclusion of the cohomology, and we have the contracting homotopy, which is this partial inverse to the Q, which fulfill the obvious relations. So since this is the partial inverse to Q, Q is degree 1, so this is degree -1. And obviously, so this is the projection to the physical state. So if composed with Q, it should be 0. If it's composed with I in this way, it is 0. It squares to 0. And these are these other side conditions, which are like similar between the Q, P, and I. These are these same relations for Q. But the important thing is that it is really a contracting homotopy. So this is the most important piece of the data. Well, maybe I jump ahead. You can think of K as being the propagator, right? The inverse, partial inverse to Q. And you need do a little trick which goes under the name of a tensor trick. You have to lift this contracting homotopy from the underlying vector spaces to the functions, because we would like to apply it to our action, which is a function, so we need to lift this to the functions on our underlying vector spaces. And there are explicit formulas how to do it, going back to fathers of homological algebra, I guess in Eilenberg standard book or somewhere you find the formulas. So they are kind of, some of them are obvious, because of course you would like to extend Q as a differential, so that's easy. The P and I, this should be projectors, so, and algebra morphisms, the only tricky part is the K, which does not extend as a differential. Okay, so there is a way how to induce new contracting homotopy projection and injection and new differential from V and H to the functions. And I will keep the same notation for these. So I hope this will not cause any confusion. Now, what we can do, we can perturb Q now by Batalin-Wilkowiski delta, and using homological perturbation lemma to form a new special deformation retract. And this is the explicit way how you do it. So what you get here is, of course, the new differential, which is performed. Well, it squares obviously to 0. It's not the derivation because delta is second order, but it still squares to 0 because Q squares to 0, Batalin-Wilkowiski delta squares to 0, and they anti-commute. Now here we get something, for which we have the formula. So if you plug in the formula, which I didn't, put here, what you get is exactly the restriction of the Batalin-Wilkowiski delta to the cohomology here. And you have the new projection, new inclusion, and new contracting homotopy. So these are all simple geometric series. And the same would be for the general formula for the perturbed Q. So in particular, what we have that, again, this new projection now intertwines between the perturbed differential and the Batalin-Wilkowiski delta restricted to H. And from this, we immediately see that if we have an interaction part of an action which fulfills the quantum master equation, this gives us immediately a solution to the quantum master equation on the cohomology, which is, this is the formula, and this is exactly the effective action which we would compute using Feynman integrals or Batalin-Wilkowiski integrals. So that's the way how to do in this setting of homotopy algebras, the homotopy transfer or computing S matrix, whatever name you prefer for it, or effective action. So as I said, in physics you would maybe talk about effective action or S matrix, and in mathematics about the minimal model for the corresponding quantum L infinity algebra. So what you have is a map which starts with a solution of the quantum master equation on V and produces one on the cohomology. And these maps can be shown to be it follows from the construction. It is a quasi-isomorphism. This means it is an isomorphism on the cohomology. Actually, homological perturbation lemma tells you even more. It gives you directly the decomposition theorem. So this is the new contracting homotopy with the perturbed differential and with the new contracting homotopy and new projection and new inclusion. And you just apply it to the exponential of the action. And since the action itself satisfies, should be interaction part of the action. Sorry, the index I is missing. And since you have a solution of the master equation, you don't get anything here. And what you see is that the difference of the exponentials of the effective action and of the interaction part is like exact with respect to this perturbed differential. And this is a little theorem that from the exactness, it immediately follows that there is a canonical map on your underlying vector space, which is nonlinear. It is a diffeomorphism starting with the identity, which preserves the Batalin-Wilkowiski bracket and maps the semi-density which you form with your original action on V, and the semi-density, semi-density on the cohomology, no typo, sorry, that's correct. That's the semi-density, again, where here you have the effective action. But you know this from Batalin-Wilkowiski that if you have a change of coordinates or field definitions on solutions of the master equations, there is an extra piece, right, in the quantum case, which is the 1/2 of logarithm of the Berezzian of the change of coordinates. And well, this is coming here from the fact that you are not pulling back the action themselves about these semi-densities. And as I said, okay, so a theorem which you can formulate precisely, at least in this case, because you are dealing with this degree-wise finite dimensional vector space, that if you take your exponential of your action and do what you would do, really compute these integrals, which are now, okay, products of finite dimensional integrals. So you gauge fix. This means that you remember our original vector space was a direct sum of the cohomology of the image of Q, which I denoted as B, and this kind of co-image piece in the complement of H. So the gauge fixing just means that you put all trivial fields which are in image of Q to 0, and you integrate over non-physical, over the C. Because these are fields which propagate. And what you get at the end is some function on the cohomology. And what I claim, it is the same thing as you would obtain from homological perturbation lemma. Not computing integrals, but using explicit formulas coming from homological perturbation lemma. Yeah, so maybe this is a little remark here, that as you see that this effective action comes as a result of the filter definition and the projection to the physical state, which relates actually the Batalin-Wilkowiski bracket, intertwines between Batalin-Wilkowiski bracket on your original vector space and on the cohomology. So now there is a natural question to ask. What is a category of Batalin-Wilkowiski theories, or equivalently of quantum L infinity algebras, such that this minimal model construction and decomposition theorem will correspond to morphisms in the category? There will be examples of morphisms in this category. So from the above, it is natural to start considering Poisson maps, because also the minimal model and the composition, these were Poisson maps. But you may object it is a bit too restrictive, because if you think of Poisson maps, they go only in one direction with respect to the dimension. So the question is whether we can have something better, and this gets us back to some actually seminal work of Weinstein about the category of symplectic space, symplectic manifolds. But before I go to that, maybe I can motivate this still a bit. Okay, so how we can interpret what I said, this minimal model and its decomposition theorem? As you've seen, the kind of important thing was split with this combination, with the half density which you form with the help of Batalin-Wilkowiski action. So, for example, in the minimal model, what you can consider is a subspace in the product, or submanifold product would be subspace in plus. So I'm sorry, switching notation between manifolds and spaces. So we had our starting vector space, the big one, where we did formulate our Batalin-Wilkowiski theory and the action, and we have the cohomology where our minimal model lives. So we can consider the symplectic manifold formed with like a product of these two, where this minus means that we take the difference of the symplectic forms. So this is minus the symplectic form on V and plus the symplectic form, its restriction to the H. Hence, so we have now two copies of H, because one copy we have here, there is another copy inside of V. So we can consider, and in V we have also this C, right? The non-physical states, right? So just, it's a trivial thing, counting the dimensions and thinking a little bit of what the Poisson structure here is. And then what you have is a Lagrangian submanifold L inside of this product manifold. Hence, if we now multiply our density with the Dirac's delta density supported on this Lagrangian submanifold, so what we get, now we have two half densities combined on V here. So we have density actually on V, and we can integrate this object here over V, right? Because one half density here and another one here. And what we get is a half density of H. on H. And yeah, this half density, well, it is not surprising that this is the half density of H, which is formed by, with help of the effective action. So this is another way how you can interpret this Batalin-Wilkowski integral or minimal model using half densities supported on Lagrangian submanifold on the product space or product manifold. Similarly, for the decomposition theorem, you remember the decomposition theorem essentially was a field redefinition. So you have a map, a diffeomorphism map from V to V, so you can look at the graph of this map inside of this symplectic manifold, and it is again a Lagrangian submanifold. And you can just think of delta half density supported on the graph of that manifold, and trivially, if you multiply your action with this delta function, it just tells you that what you do is really, you are doing pullback of your half density, and this is the minimal decomposition theorem. So this would kind of, and maybe before I go ahead, I also should mention that all half densities I have now introduced, these are closed under the Batalin-Wilkowski delta. So it's, you can extend Batalin-Wilkowski delta from functions to the half densities in obvious way. So locally, you do it, like you apply delta in local coordinates to the function, and then you show that the definition is correct. This was Kudavedrian, contribution to, one of his contributions to the subject. So all these half density were BV closed. So now this brings us to the subject of quantum odd symplectic category, which is due to Chevera, and it is an odd version of the Weinstein's symplectic category. So Weinstein was the first one who suggested that, well, it's not really category, but that what we should consider is Lagrangian submanifolds in the product of inside of products of symplectic manifolds, taken one with the opposite symplectic structure. So in this odd symplectic setting, which is relevant for Batalin-Wilkowski or quantum L infinity version, is that, and this is the enhancement actually done by Chevera, you don't consider only, you consider half densities on the product of symplectic manifolds. So here, not necessarily they are not necessarily supported on Lagrangian submanifolds, but you can, you can consider half densities on the products of the symplectic manifolds, where now, so this would be the morphisms. And so the composition is obvious because now you have two half densities on M2, which you combine together in a density. So what you get, you can integrate a density over M2, and you get again a half density on product of M1 minus times M3. So that is the composition. Right. And of course, it is, from my previous discussion, it's kind of interesting or important to consider the action of Batalin-Wilkowski operator on the densities. And the point is that, yeah, as I said, Batalin-Wilkowski acts on semi-densities and sends a semi-density into semi-density. And so this is the Severa's proposition that in this quantum out-symplectic category, if you compose two delta-closed morphisms, you get, again, a delta-closed morphism. So that would lead us to preliminary definition of what the morphism could be if, we would like to talk about morphisms of Batalin-Wilkowski theories. You remember that now in this setting, we had our odd-symplectic vector space, but slightly generalized version, odd-symplectic manifold, and the solution of the quantum master equation, which is a delta-closed element on semi-densities. So remember, we formed these semi-densities using e to the exponential times the semi-density on V, which comes from the Lebesgue measure on V. And we could say that morphism between two Batalin-Wilkowski theories, one on M with semi-density F and one on N with semi-density Q, would be defined by a delta-closed semi-density on the product, such that if you integrate, here you naturally have inside a density on M, so you can integrate over M. This would you give the other semi-density on G. And I hope it was clear from my discussion of the minimum model and the composition theorem that these two examples fit into this definition. So I gave you actually this semi-density. These were these delta supported semi-densities on the correct Lagrangian submanifolds. But now we somehow destroyed the symmetry between the two theories because we integrate on one side and go to the other side. So we lost something. So now the question is whether we can improve it a bit. So now I go to some part of my talk, which is still not finished. It's still under construction. Essentially, I give you a proposal what we try to do, and for that, I keep it simple. I would just consider only the linear category. So here I would consider only vector spaces and linear maps between vector spaces. And linear and correspondences or Lagrangian submanifolds, Lagrangian relations which are subspaces, vector subspaces. So if you take two vector spaces and you form this product or plus vector sum, and so what you can easily prove is that whatever your Lagrangian subspace here is, it is necessarily of a specific form. So it is a product of something which is an isotropic subspace in M, isotropic subspace in N, and a graph of a linear map which is isomorphism, actually. So how this comes from? point is that you can look into the image and co-image of the Lagrangian correspondence, and you can see that you have this immediately. You see that you have this isomorphic isotropic subspaces here, and so what you can do, you can do the symplectic reduction. So you look at their symplectic complements and you factor, and you get symplectic subspaces in M and N. And it is an easy exercise to show that these two have symplectic vector spaces are necessarily isomorphic. So what you now can do using that is that because of the specific form of each Lagrangian correspondence, if you look what this integral is, you easily see that what you get actually is a half density on n with a function which depends only on this symplectic subspace. So essentially what you do is you integrate only over m, and the rest of integration is integration over this graph, which tells you that you do change of coordinates from Tm to Tn. So this way you see that if according to this prescription, what you get is really a half density on n, but actually it depends only on this symplectic piece of the n. And similarly, you can do vice versa. You can integrate here the ESM with respect again to this delta two-parted function on the same Lagrangian correspondence, integrate over n. It's completely symmetric now, so what you get is you get a half density on m, where the action will depend only on the symplectic piece of m. So what you can now propose is a reasonable thing, is you ask for a morphism between these two Battalion-Wilkowski theories, or quantum L infinity algebras, is that after doing these two integrations, once leading you to an action on the symplectic piece of m, and once the symplectic piece of n, which you get after symplectic reduction, that these two have to be related by the field redefinition given by this phi. So in this, shortly speaking, you integrate along two different fibers, like isotropic subspaces in n and m, which are canonically given by L. So you get two different actions on two isomorphic symplectic vector spaces, and you ask them to be related by this change of coordinates, again given canonically by the Lagrangian correspondence. So in this sense, two equivalent theories, should be related by field redefinition after integration over these two fibers. So what is the, despite of the fact which I didn't mention, that this symplectic category of Weinstein has the troubles, and the same is in the graded setting, that if you compose two Lagrangian correspondences, you don't get necessarily Lagrangian correspondence. This is fine in the linear category, but in general for manifolds, yeah, you don't get necessarily a manifold by composition. Here it's even worse because already in the linear case, it is not true that if you have one morphisms and another morphisms that they would compose to a morphism. Well, but there is if and only if condition, which you can easily find out chasing the diagram of correspondences. So once we have this correspondence here and its decomposition, and we have another one and it's this decomposition, we can compose, of course, these two correspondences to get the correspondence here, and we know that again it decomposes. And for the composition of these two things work, it is necessarily that if you do two fiber integrations from here to here, one along, well, you can invert this one, obviously. It has a partial inverse, so use the partial inverse. So you can integrate along this fiber or this fiber. And if you get the same thing up to this change of coordinates, then the composition works. And so this, you know that this will be, for example, true if you can smoothly deform this Lagrangian subspace or some submanifold in general into this one. But if not, well, okay. Doesn't need to be true, this equality. Okay, do I still have a few minutes? Okay, so maybe based on that, one can think of what would be kind of a notion of T-duality between two Batalin-Volkovitsky theories. So, okay, you have seen this picture with the correspondence space, like in, for example, Christian talk. So, suggestion would be that we would say that two Batalin-Volkovitsky theories are T-dual if we can find another theory such that we have two symplectic reductions. So this double fibration, such that the action here and here are obtained from this action here by the integration along the fibers. And again, essentially it's the same type of thing as before. You may ask whether these T-dual actions obtained in this way from the parent action, whether they are related by a morphism in my previous sense. And it is not necessarily true because, again, you have these two correspondences, these two reductions. This is the partial inverse. So what you can do is, of course, you compose these two, you get another correspondence, and then you decompose it according to my prescription. And for these T-dual actions, it is necessary, if they should be kind of equivalent in my previous sense, that these two fiber integrals going from here to here should be the same, which again, we know only in the case if these two Lagrangian subspaces here or submanifolds would be related by in a smooth way. Okay, so, well, this was all kind of now in the language of Batalin-Volkovitsky theories, but you can interpret everything using the homological perturbation lemma, you can forget about the Batalin-Wilkowiski and formulate everything in terms of just algebraic language of quantum L-infinity algebras about these maps. Of course, since here what I said was kind of restricted to the linear category, so you think a bit more about how to extend it to the general setting of odd-symplectic manifolds. Because, for example, you know, from the decomposition theorem, we had the relation between the action and its decomposition, but it was a non-linear map. So somehow, naturally, already within the linear odd-symplectic category, non-linear maps pop up out naturally. So one would have to ensure that everything what works here and would work on like locally for manifolds on the level of tangent spaces, that, you know, everything would make sense, all these integrations and all these reductions, etc. But yeah, it's not so difficult to formulate the conditions, technical conditions under this would work. At least, as I said, in this finite dimensional case. Of course, if I go to infinite dimensional case, to the true quantum field theory, I would have to make sense out of integration along non-compact directions and all these things. And of course, renormalization, etc. Okay, so that's essentially, yeah, what I wanted to present you today. Thank you for your attention.
Thanks for Brano.
Brano, could you please summarize the difference between Chever's symplectic odd symplectic category and the category that you introduced?
Oh, okay. So let me see. Chever considers only semi-density on the product. Where was it? No. Yeah, these are dimorphisms in Chever's category. Whereas I ask more, well, no, there is no action here.
Mm-hmm.
Well, actually,
but
yeah.
Can't you consider semi-density as an action?
Yes, that's true. That it is inside here somehow, because if you consider like a point here, yeah, and a Lagrangian subspace in the product of point and M and semi-density on that, you get an well, essentially, that would be a particular example of a semi-density. Yeah. So it is kind of included also.
I see. And is this category a true category?
No. Again, it's not. It has the same problem as the Weinstein's category.
But there are no Lagrangian submanifolds that you talk about here in this category. It's just densities, semi-densities.
Yeah, that's correct. Sorry, that's correct. Yeah.
So
that's correct, yeah. So you would have to specify that, yeah, okay, Weinstein's, and this was kind of implicitly in my construction for that, I would consider Lagrangian subspaces and densities supported on Lagrangian subspace.
Mm-hmm. But if you just consider densities, then it's a true category. You can compose two more.
Oh, yeah, sorry. That's right? Perfect. Yeah, it works.
But and what is? But this was Chever's category. Now, what do you add in your category?
Oh, okay. So in my category, I would like to
just again remind.
Yeah.
To
okay.
slides.
So yeah, in my category, actually, I would like equip also this M and N with actions. So as I said, you can view this also if like semi-densities in Chever's sense on the product of a point and M. but yeah, I make it more explicitly. I would like to have an action here and an action here. And okay, I would consider densities here which are supported on Lagrangian subspaces.
But if you don't require support on Lagrangian subspaces,
This works. Yeah.
it looks like
it
the
works.
goodness category.
Yeah.
Right? So what you add as compared to Chevre is the delta closure condition, or what's the?
Well, actually, I think he also considers delta closed. Yeah, he considers also delta closed. So no, yeah. So my little addition would be what did I do? No,
Apparently
I'm sure there are mistakes in spelling for sure. But yeah, so I made it, I think, a bit more explicit, and I ask this integration going on, closed semi-densities here, which are supported on Lagrangian subspaces. That's one thing.
What was F and G or Q? What was F and G actually?
Yeah, so you can think in my setting, F would be half density E on S M times half density on M, the Lebesgue half density on M, and G would be E to the S on N times half density on N.
Also, the notion of a morphism adds. No. Oh, I see. So there are half densities on M.
Yeah, these are half densities. Yeah,
okay.
all half densities. Well, at least in this linear category.
The objects are also different, not only the morphism.
Yes. Also objects are different. Yeah. The objects are different.
I was just confused.
Yes. No, the objects are different. Also, this condition on Lagrangian support. And yeah, and this is this refinement that you don't just integrate one, but you use this this general feature of Lagrangian subspaces, that you compare the things only after integrating out these two fibers.
Okay, yeah, thank you very much for clarifying this.
Yeah, oh, thank you for asking. Maybe it wasn't so clear so for my presentation.
Looks there are no other questions. Maybe quickly. Okay. All right. So in the interest of time, want to close. Yeah. Thanks.
Oh yeah. So thank you
so much.
Thank you for the attention. Yeah.
For the nice talk.